Hi folks, this week's vlog is going to be a bit of a continuation from last week where we focused on mental accounting and framing, except this time we're going to use a slightly more complex example that uses weighted probabilities. In traditional economics, we assume that humans use a formula to weight the costs and benefits associated with a choice to find the expected utility they would receive from each possible outcome. For example, let's say there was a situation where you could complete a survey and receive $5, or you could complete the survey and be entered in a raffle where you would have a 10% chance of winning $50. Or a 90% chance of winning nothing. In option A, if you complete the task, there is a 100% chance that you'll get $5. 1 times 5 equals 5. In option B, you have a 10% chance of receiving $50, so it's 0.1 times 50 equals 5. In both cases, you have an expected monetary reward of $5. You should be indifferent between these two choices if utility is measured just by the money received. Side note, indifference is the term that economists use when two options will provide the exact same amount of utility. If you get the same amount of utility, then it shouldn't matter to you which one of these choices is received or chosen. If it doesn't matter, then you're indifferent. But you wouldn't be indifferent, would you? One of these outcomes is certain, and the other one involves a risk, but with a large reward. The expected utility model relies on 4 key premises: cancellation, transitivity, dominance, and invariance. Those concepts are a bit complicated, so some explanation is required. Cancellation is the idea that the choice between options should only depend on the states that result in different outcomes. That means you could have a bunch of different choices, but the ones that have the same outcome should cancel out, so you're faced with a decision between options that have different outcomes. So if I'm deciding where to get groceries, and Google Maps gives me routes to 3 different grocery stores and several different route options to each grocery store that all take the same amount of time, the only decision I'll care about making is which one of these different grocery stores I should go to. Transitivity refers to the ability to represent preference by an ordinal utility scale. This is a fancy way of saying that you can rank your choices by the amount of utility you expect to get. Think of the transitive property in mathematics. If A is greater than B, and B is greater than C, then A is greater than C. Or if I like cherry jello better than lime jello, and lime jello better than strawberry jello, it should hold that I would prefer to eat cherry jello more than strawberry jello. If I said that I like cherry jello more than lime, and lime more than strawberry, but I like strawberry over cherry, that would be irrational since my preferences were not transitive. Dominance is the idea that if one option is better than another in one state, and at least as good in all the other states, then the dominant option should be chosen. For example, if you're deciding between 3 jobs that are all in the same field, and they all pay the same amount, and you're uncertain for all of them about whether or not you'll get along with your coworkers, but one of the jobs offers better health insurance, then you should choose that job because it is better than all the other jobs in one aspect, and at least as good as all the other jobs in every other aspect. And finally, invariance. If you're given a set of choices, different representations of those choices should yield the same preference. Let's say I asked if you would like a green apple with a 5% chance of a worm, or a red apple with a 95% chance of not having a worm, and you chose the red apple. If I had said you can choose between a green apple with a 95% chance of not having a worm, and a red apple with a 5% chance of having a worm, you should still choose the red apple, because the probabilities have not changed, only my description has changed. The expected utility model is captivating because of its simplicity and power. However, in their article, Tversky and Kahneman illustrate the failures of this model when it comes to predicting human behavior. In the 1980s, Tversky and Kahneman gave a questionnaire to 72 physicians attending a meeting from Medical Association. On that form, it described a scenario in which a 40-year-old man had a tumor that would result in his death within a month if action was not taken. 3 cases were offered, and in each case, 2 options were presented. In the first case, treatment A gave a 20% chance of imminent death for the patient and an 80% chance of a normal life with an expected longevity of 30 years. Treatment B gave the certainty of a normal life with an expected longevity of 18 years. In the second case, treatment C gave an 80% chance of imminent death and a 20% chance of a normal life with an expected longevity of 30 years. Treatment D provided a 75% chance of imminent death and a 25% chance of a normal life with an expected longevity of 18 years. In the third and final case, there was a slightly different adjustment to the scenario. There was a 25% chance that the tumor was treatable and a 75% chance that it was not. If the tumor was not treatable, death would be imminent. If the tumor was treatable, then the outcomes of the treatment could be one of 2 options. Treatment E offered a 20% chance of imminent death and an 80% chance of a normal life with an expected longevity of 30 years. Treatment F gave the certainty of a normal life with an expected longevity of 18 years. Now, what's pretty interesting is that the second and third cases have the exact same probability, but in the experiment, the preferences for these treatments were swapped in the second and third cases, so the physician's preferences changed based on how the question was asked. Let's review. In case 2, 68% of the physicians preferred treatment C, which risked an 80% chance of imminent death and a 20% chance of a normal life for 30 years, over the 32% of physicians who preferred treatment D that would have had a 75% chance of imminent death, and a 25% chance of a normal life for 18 years. In case 3, the scenario was altered a bit so that there was a 25% chance that the tumor was treatable and a 75% chance that the tumor was inoperable. If the tumor is inoperable, then death is certain. Having read that, 32 of the physicians chose treatment E, which gave a 20% chance of imminent death with an 80% chance of a normal life for 30 years, and 68% selected treatment F that offered the certainty of a normal life with an expected longevity of 18 years. Understanding the base probabilities present in case 3, though, we know that the probability of death is the probability that the tumor is treatable times the probability of death during the treatment, plus the probability that the tumor is not treatable. To find the probability of death, given that the tumor is treatable, we multiply 25% by 20%. Now we add that to the probability that the tumor is not treatable, which is 75%. So taken all together, the weighted probability for death for treatment E is 0.25 times 0.2 plus 0.75, which equals 0.8. The probability of death is 80%. The probability of life is the probability that the tumor is treatable multiplied by the probability that the treatment will be a success. 0.25 times 0.8 is 0.2, so the probability of life is 20% with an expectation of a normal life of 30 years. For treatment F, we know that there is a 75% chance of imminent death if the tumor is untreatable, and a 25% chance that the man will have a normal life for about 18 years if nothing is done. These are exactly the same probabilities as treatment D, but in the second case where treatment D was an option, only 32% of the physicians selected that option. Treatment F sounded like it would ensure survival, but in reality the assurance is conditional on the probability of the tumor being treatable. Since the probabilities were non-transparent in the third case, the decision-maker's choices are inconsistent depending on the framing. Thus, the premises of the expected utility model do not hold, especially the invariance and transitivity principles. Humans aren't very good at calculating expected utility because sometimes we have trouble remembering to take base rate into our mental calculations. And once again, we see that the framing of our choices can influence how we perceive potential outcomes. After viewing today's episode, I hope you have a more informed understanding of the expected utility model and how humans misinterpret and miscalculate probabilities.